So today we are here with Rob Weryk, who works with the Pan-STARRS project in Hawaii. Carl Hergenrother and I are going to interview him, have a discussion on behalf of the ICQ Comets and Their Cousins YouTube channel. We're very pleased to have you here today, Rob. Thanks for joining us. Can you tell us a little bit about your background, how and when you got into astronomy, and what your career path has been?
Yeah, for sure. So I'm from southwestern Ontario in Canada. My career path, in high school, I had very inspiring science teachers. And so I knew from that age that I definitely wanted a career in science. Originally, I was interested in chemistry, but when I took physics, I realized it was the physics aspects of chemistry that I really liked the most. I ended up pursuing my undergraduate degree in physics at the University of Western Ontario. Um, I actually, in my last year of high school, had a co-op placement with the meteor physics group at Western. So that kind of gave me some early experience into research, and I really liked that. So after doing my undergraduate degree, I also did my undergraduate thesis project on looking for interstellar meteors with a radar system that's located here in Canada. And I really was interested in the meteors, and I knew I wanted to study that professionally. So I stayed at Western for my PhD. My PhD itself was also on meteors. I studied simultaneous observations of meteors using both a radar system and video camera system to kind of better constrain the relationship between electron and photon production. After that, it came time to look for a postdoc. I did a brief postdoc in Eastern Canada with Bob Hawks at Mount Allison University. After that, I was just applying for different postdocs. There was one at the University of Hawaii to work with the Pan-STARRS project on near-Earth asteroids. So I applied for that, and I got that, and that's how I ended up in Hawaii.
Okay. So you've been with that program for a while, and you moved back not too long ago to Western Ontario. But are you still working full time with Pan-STARRS, or is that just a part-time gig right now?
No, so my position is funded through Pan-STARRS by the University of Hawaii. There's still a lot of work to do with that. I'm very interested in working with the project, but I'm based at Western now, funded by Pan-STARRS itself to work for them.
I see. Okay. So tell us a little bit about your interest with comets generally, and how you kind of got into. You seem to be sort of the point man for comets at Pan-STARRS. Did that come out of your own interest, or were you appointed that position? How did that work?
So I mean, I've always had an interest in comets. From my days of studying meteors, all the meteor showers are produced by comets. At least the major showers are. So there always was an interest there. At Pan-STARRS, one of my main responsibility is reviewing the new candidate detections, trying to find the near Earth objects. So it's really part of that study that the comets come about, trying to identify new comets when they're just barely visible in the images, and trying to figure out which ones are comets and which ones are not. So that's really where it came from there.
Okay. So do you have an algorithm that picks things out as possibly extended?
So when you review the Pan-STARRS candidates, it basically is presented on a web page. There's kind of like a subpage that has some a ranking based on like the moments of the PSF fits. So it kind of tells you objects that might be possible comets, but it doesn't always get them. So it's really a question of you looking at the images of the comets and picking out which ones you think are actually new comets. So this can be quite tricky to do. Sometimes we're not sure. We have to follow it up with the Canada, France, Hawaii telescope to actually be sure they are. So it's very much a visual inspection to see them.
Right. So you have an ongoing program with the Canada, France, Hawaii telescope where you have time and you can access that on a regular basis.
Yeah, we have time every semester. The main purpose is to help confirm our near Earth object candidates, but we also use it to confirm cometary activity. CFHT being a 3.6 meter telescope, it's very good at detecting, faint coma.
Right. Yeah. So for the audience who doesn't know, Pan-STARRS has its name on more comets now than any other survey program. It's by far and away the leader in the field. Do you keep a running tally of how many Pan-STARRS comet discoveries you have?
I used to, but I lost count. It's quite a number. Chances are, if you see a comet pan-STARRS, I was the one who originally sent it in.
Yeah, yeah. So who else works on pan-STARRS with you regarding comets, and who are your closest colleagues at pan-STARRS?
So there's really just three of us that take care of visually confirming our new Canada detection. So Richard Wainscoat, he's in charge of the NEO search effort. And then there's two of us, myself and then Yudish Ramanjulu. So we're the one that really actively review the data and try to pick out the comet candidates.
Okay. Is Yudish a doctoral student, or what is?
Oh, he's a researcher position. So
Okay.
yeah, he's been there since 2015.
Let's look at one example. 2016 BA14 was recovered recently by yourself as 2016 U6. What prompted you to look for this comet now a year and a half after perihelion, and likewise with some other comets that you look for in archival data?
Yeah, so usually picking out a second apparition of a comet, there's kind of a direct trigger. Either a colleague is interested in it, or there's some other scientific interest. So for BA14 specifically, there was a possible meteor shower outburst that could have been associated, a never before observed shower. So I have a side project that I use the data from the Southern Argentina Agile Meteor Radar. So it's capable of detecting meteoroid orbits every day. So trying to see if there's a shower outburst from this comet, there ended up not being, but that led me to search for the object in archival images.
Okay, so is this a daily thing that you do, where you're looking at the pan-STARRS imaging?
Yeah, every day that we operate, which is most days, I have to review the data the following morning. So one benefit of being in Ontario is right now it's 6 hours ahead of Hawaii time, so we're able to follow up our candidates, closer to real time when they're actually observed and processed by the software.
Right. Yeah. Okay, that's good. Carl, you had some questions about his meteor program.
Yeah, going back to the meteor research. I mean, you talked about it a little bit, but what in particular was the focus of your research? Was it mostly the interstellar meteor work, or were you helping with the software as well?
So my main focus with meteors is radar meteors. So these are VHF all sky pulse radars. You transmit shape pulses, they reflect off the ionized trails. And you can actually detect many, many more, thousands and thousands of meteors every day. Well, way more than you could with any visual-based system. So these give you the number statistics to really delve into certain topics that you just can't really do that well with camera systems. So one of the early projects I did was looking for interstellar meteors. So, meteors that originated from outside the solar system. This is really tricky because there's questions of uncertainties on radar meteors. It's not like it is on asteroid observations. They're a lot less precise. So you really have to have a large number of meteor samples to actually go through. So that's my main focus, was radar meteors and then looking for interstellars specifically.
Was this mostly with the, I guess it's the Seymour, the Canadian Meteor? I'm not sure
Yeah.
what the acronym, yeah.
Yeah, so the Canadian Meteor Orbit Radar.
Right.
So these are based on their VHF atmospheric wind radars. So basically, they're sold commercially to study the winds in the middle atmosphere. They do this through meteor observations, but you can actually use them for astronomical purposes too. So they've basically been modified for those wind measurement systems to be able to measure Keplerian orbits for meteors. Yeah.
Oh, and so these meteors actually need these radars actually need the meteors to measure the atmospheric winds.
Yeah. So basically, you reflect off the trails, and the trails
Right.
get blown by the middle atmosphere winds, and that actually shows up as like a Doppler measurement in the phases that you can detect. Yeah.
So how many meteors, say, nightly are usually detected?
So Seymour would get about 3,000 per day. The SAMR system in Argentina can get about 10,000 per day.
And these must be meteors or meteoroids that are significantly smaller than what we would see from our backyard visually.
Oh yes. These are all like sand-sized particles, so quite faint. If you're out in the country, on a dark summer night, then maybe the faintest ones you would see would be kind of the brighter ones that the radar could see.
Great, great. And so, you mentioned that, of course, you're interested in comets, you're interested in meteors. What is kind of the synergy between the two studies, or at least the work that
Well,
you're doing?
it's they're related. Comets and asteroids produce meteoroid streams, which can intersect the Earth and make meteors. So that's kind of what led me from a meteor career to more of an asteroid-based career. So I'm very much interested in the comets, but they are kind of the second fiddle to the asteroid work.
Mhm.
The main focus of what I do is finding the hazardous near Earth objects.
So for asteroids now, I mean, we're discovering that almost all bodies are releasing material at some level. I was on OSIRIS-REx, so I was there when we were at Bennu, and we were seeing these particles being, constantly thrown off the surface of the asteroid. From the radar work you're doing, I mean, how much of a contribution are the asteroids making to the meteoroid population?
It's there is contributions. There are special cases where it's not clear exactly what the parent object is. So the Geminid meteor shower, for example, it comes from Phaethon. Is Phaethon an asteroid, or is it some kind of extinct or dormant
Yeah.
comet? So
Hmm.
there is still a lot of research to be done in that kind of question. But certainly there is contribution from asteroids. Bright fireballs that all-sky camera networks see, for example, those would be more asteroidal in origin. So,
All right. So speaking of bright fireball networks, I mean, there's several of these all-sky fireball networks being set up around the world. And then there's a lot of groups now, like Peter Jeniskin's group, as well as some amateur groups that have, cameras that are looking for more of like meteor shower type monitoring. What do you see as being kind of the advancements that will be made over the next couple of decades, especially for amateurs in backyard work? Or can you even see amateurs kind of going into the radar realm? I know a lot of them are doing radio work, but maybe even infrasound and radar as well.
yeah, I mean the radio work that they do is it's kind of different from radar work specifically. One thing with radar, part of the acronym is the ranging part.
Mhm.
So there's that aspect that you can't do with radio stuff. I kind of see video meteor networks as kind of a solved issue. I actually wrote the one system that the NASA is using at the Marshall Space Flight Center for their system.
Is that Asgard?
Yeah, that's the Asgard
Yeah.
system. Yeah, so I wrote that in early grad school. The detection of these objects, it's kind of a solved issue. Back in the day, it's kind of a question of coverage. Now there's
Mhm.
a lot more coverage across the globe, but it really has to be the next step, which is, okay, you have all these detections. What can you learn scientifically from that? And that's really where there's still a lot of contributions to be made, I think.
And what can we learn from those that we haven't already
Well,
learned?
well, it really depends on your camera system. There's how accurately you can do it. Measuring like the deceleration lets you work out like what the bulk density could be. So there's still a lot of physical quantities that, even though people have measured it for specific cases across the spectrum, it hasn't been done for all meteorite droppers, say. And it really is a question of, you know, with an all-sky system network that you're detecting these meteorite droppers, the sample kind of comes to you, so you can actually study it in your own laboratory, basically from your backyard, almost. Yeah. So there's just expanding the data set that's been analyzed like this is really what the next steps are.
So you got an interest in interstellar meteors. Do you think, I mean, maybe this is a little bit of a contentious question, but do you think there's a possibility of recovering interstellar material from an interstellar meteorite dropping?
Uh, I mean, it depends. Off the top of your head, you might think, oh, an interstellar meteoroid is expected to be very fast, but that's only with respect to like the sun, say. If you had a interstellar meteorite that kind of caught up with the Earth, it could actually be moving quite slow in the atmosphere. So it is theoretically possible that it certainly has the speed that could drop a meteorite. It would be a question of material strength. So I think a lot more research would have to be done on that.
And these interstellar meteors, is it just material that's kind of been ejected from another solar system, or is it in some cases stuff that's being blown out by basically the solar wind of these other stars?
Oh, it could be both, for
Both.
example. Yeah,
Mhm.
there's still a lot of work to be done on that too. It's the first step, at least with the radar studies of interstellar meteoroids, is really detecting reliable streams of material, and that hasn't been done yet.
Okay.
So when I talk to people that work both with meteors and comets, I'm always interested to ask the question as to what you think about the possibility of cometary meteorites on the ground on the Earth. There certainly are pieces of comets on the Earth, but it's a very contentious debate. It's kind of been sort of ruled out that carbonaceous chondrites are from comets, based from analyses at spacecraft analyses at comets. But what do you think, Rob, about the possibility of our having pieces of comets in our meteorite collection on Earth?
I mean, I honestly haven't done much work on meteorites themselves.
Mm-hmm.
So it would be more a question of, okay, present to me the tests you could make to conclusively tell one way or another, and
Right.
review that and see are they plausible. But I myself haven't spent much time working on meteorites themselves.
Right. But it seems to me plausible that we've got some pieces of comets on the planet, and whether we have any in meteorite collections is not fully solved. But
yeah, you can do the ablation modeling to see, is it possible for this material to survive to the ground? And if you can do that, then it seems like it would be quite plausible.
yeah, great. So just getting back to Pan-STARRS, I just wanted to ask you to just quickly review a little bit about the history and the telescope itself, and the survey program, and like how far into the future is it thought that it'll go?
Oh, as to the future, that entirely depends on the funding. So historically, there was what we call the old science consortium. They called it the 3Pi survey. They observed as much as the sky over and over in the GRIZY filters. So this was to make a general astronomical database. It was suitable for a wide range of research purposes, cosmology, stuff like that. The solar system component originally was a very minor aspect. Since I think it was 2014, Pan-STARRS has actually become funded 90% by NASA's Near Earth Object Observation Program, to actually focus exclusively really to that 90% level of finding new near Earth objects. So with the current new consortium, it's basically 90% NEO dedicated survey, and that's really the goal that we have now. So as long as NASA is willing to fund that through Pan-STARRS, we'll proceed for as much in the future as we can.
Right. So how do you see the future of Pan-STARRS with the LSST coming online, for example, which is going to go deeper? You can right now, Pan-STARRS can routinely get down to about 22nd magnitude.
Yeah, we can get to 22nd. For nights that there's really good seeing, you can see 23rd magnitude in the images. There's a few cases where the seeing is so exceptional you can get to 24th magnitude. That's very rare, though. In terms of how we fit in with LSST, I mean, the two surveys are very complementary. There's a huge amount of the sky we can see up north that they can't, or at least they won't be able to see. So they're very complementary.
Right. Yeah. So what are your thoughts on, as we move forward with these surveys with larger telescopes that are getting fainter and fainter, what are your thoughts about the problems of distinguishing a comet from a non-comet? In terms of, as we go fainter and fainter, it's hard to pick up coma or tail activity, for example. And a lot of things are going to just be reported and given minor planet designations. And found to be cometary later, but it seems like this is going to just increase as we move forward in time.
Oh yeah, I mean, we already have that problem now. There's cases where it wasn't recognized immediately that an object was actually cometary. Sometimes you really need a much larger telescope. So we use the Canada, France, Hawaii telescope to confirm candidates. We also visually inspect all of our new candidate objects to actually check for coma, whether we can see it or not. So there's always a question with new surveys: are they actually inspecting, what the actual point spread function, the PSF, looks like in each image, or are they just going based on an orbit after the fact? So it certainly is a concern. Yes.
Right. Will LSST cause you to modify anything of what you do, or are you just going to continue to do exactly what you're doing now with PanSTARRS?
Oh, we'll just continue to do what we're doing now. Yes.
Yeah. Okay. Are there any other projects that you're working on besides the meteors and the comets? Are you teaching at all?
Oh, no teaching. My position is purely research focused.
Okay.
Yeah.
Okay.
So it's really just the discovery of NEO objects, study of interesting objects that we find. In terms of comets, we're always hopeful that we're going to find the next great comet. We want
Right.
that to be called PanSTARRS.
Right.
Yeah.
Instead of ZTF or something like that.
Yeah.
It's a better acronym.
Yeah.
So of all the comets you've discovered at PanSTARRS, do you have a favorite or a few favorites?
Well, I mean, there's always the special case of Oumuamua, whether that's,
Right.
Is a comet or just a weakly active comet or defunct comet. That's of course the most interesting object we have. We're always hopeful that we're going to find new ones. Now that we know that they exist, we're, every new detection we have, we look at and say, is it possible this could be a new interstellar object? Otherwise, some of the other comets, I mean, again, the long period comets, some of them, we're hopeful that one will turn out to be the next great comet.
Right.
Yeah.
Yeah. In terms of the focus of NASA, which is to find near Earth objects, it seems that all of the objects that have actually impacted the Earth so far, I think there have been 7 in the last 15 years, they've all been found very close to impact within a day or two, and they've all been thought to be pretty small, on the order of the size of a car or a bus, maybe. So it doesn't seem that we're likely to get to find something that is really large and catastrophic from the asteroidal set. And to me, it seems more likely that if we were to have a catastrophic hit, it would come from a long period comet.
I mean, I've read that the impact hazard is certainly, there's an asteroid component and a comet component, and so right now the asteroid threat is the dominant threat. And one day, it'll be a long time from now, when enough near Earth objects are found, then the dominant risk will shift to the comets. Until then, we're still very much interested in looking for asteroidal potential impactors. At PanSTARRS, we're not specifically looking at these objects that are going to impact less than a day after they're found. We want to find the larger objects that are farther out, that we have many years or even decades of warning. There still are a lot of objects that haven't been found. There's a case of if the period of an asteroid is an integer multiple of the Earth, then sometimes those aren't found like as often as they should be. So there are cases like that where no, there's still a lot of detection capability that PanSTARRS can contribute to. So we're still very much interested in finding those type of objects.
Right.
Yeah.
But as we get further along with finding these fainter and fainter objects, it seems that we're ruling out larger objects as we go along. So I don't know, has an assessment been made as to what the maximum size is likely to be of the worst case scenario minor planet at this point? Because it seems to me we're getting down to under half a kilometer in terms of completeness.
Well, I mean, there are models that predict what we should have, and we can compare those to what we find. We still find, at least 1 kilometer sized object every year, whereas some of the models have predicted we found all of them or the majority of them. So there still are some surprises. But yeah, certainly with more time, we're eventually going to find more of these objects, but that's still quite a ways away, I think, to being able to find them all.
Right.
How close to the sun does PanSTARRS search?
So normally we don't search too close to the sun. The exact limit depends. Like we can search. There's what's called the morning sweet spot and evening sweet spot chunks. So we can search those if conditions are right. But we are very much an opposition centered survey. So we spend most of our time searching away from the sun.
And how much does the Milky Way affect pan-stars? Looking for
So
asteroids.
we won't actually observe in the galactic plane itself yet. So there are cases where if you had an object that was in the galactic plane, we're not going to be able to see it until it moves outside of that. Yeah.
Right. And that's typical for most surveys, I think.
As far as I know, most of them have issues with that. Yeah. And it'll be worse for newer surveys that go fainter.
So what kind of cadence does pan-stars use for its asteroid detection?
So in terms of nightly observations, so we try to visit the same spot 4 times, spaced about 15 minutes apart, so, about over an hour. We try to return to the same spot, every lunation, sometimes more. There are, observing constraints due to the weather, if the moon is up or it's windy from one direction. But generally on a single night, we observe it over an hour.
And does pan-stars conduct any trans-Neptunian searches?
So we have looked for TNOs. So the main detection pipeline of pan-stars features difference imaging. So TNOs actually move slow enough that they're kind of self-subtracted from the images.
Right.
So they kind of need special handling. So a number of years ago, I went through the pan-stars data set and I picked out a whole bunch of TNOs. So we've had hundreds of new TNOs. Most of those were announced in 2015, 2016, that timeframe. So we can find them in the images, but it's not processed through the normal nightly processing.
Right. I figured if, repeating lunation to lunation, maybe you'd have to search between that kind of data set rather than.
Yeah. Fortunately, TNOs, they don't move very far. So they're kind of easier to link in many ways than NEO observations are. Yeah.
So, and you use 3 or 4 different filters with pan-stars, or do you focus? I notice you use a W band quite often.
Yeah, so the 2 main filters we use, if the moon is not up, we'll use the W band filter. So W is essentially G, R, and I. And then if the moon is up, we use the I band filter. I think the 2 nights or 3 nights surrounding full moon, they use the Z band filter. That's a very special filter because the moon is just too bright for that. But most of the data we want to do in the W band filter.
Right. Okay.
And the Z filter is even redder than I believe.
Yes, it's GRIZY. Yeah.
These are Sloan filters.
I'm not too familiar with the exact specifications. I think they're essentially Sloan, but there are small differences. Yeah.
Created for pan-stars?
Yeah, these ones were created for pan-stars specifically. Yeah.
Okay.
The pan-stars did discover a lot of supernova in the early days. Is it still actively looking for supernova?
Oh, they're still actively searching for supernova. Yeah. So I don't deal with that side of the data analysis. I'm exclusively on the asteroid stuff, which is what we're 90% funded for. But there are a lot of supernova and other transients that are searched for.
So what is the policy in terms of making pan-stars images publicly available? Is there a time period before they're made available? And can people access them?
So there is an archive at the Space Telescope Science Institute. So that's data from the old consortium. So it's essentially all the GRI data pre the NEO focus. There's no W-band data in it. As for the more recent data, including the W-band data, I don't know of any current plan to make that available publicly.
Oh, I see. Okay. I thought that that U.S. taxpayer-funded observations had to be made available publicly after some period of time.
I'm not familiar with the policies. Yeah.
Okay. Oh, any other thoughts?
No, we're just going to keep doing what we're doing.
Yeah.
We're finding NEOs essentially on average. It's 2 or 3 a night now. I think is maybe even 4.
Right.
Yeah.
Although that term is kind of loosely used when you get into AMORs and all these others that aren't really all that close to the Earth. But
yeah, that's true. There are some that are technically NEOs, but they don't actually come near enough. Yeah.
But well, it's great work that you're doing. I enjoy working with you in terms of announcing the new comets with the Central Bureau, and also, of course, we work with the names with the working group on small bodies nomenclature. So occasionally we have problems, and you're seeing more of this with the naming issue, because we're getting, for example, the Minor Planet Center, and even people outside the Minor Planet Center are going into the ITF, the tracklet file of one night stands, so to speak, and linking objects together, and we've had some cases where they turn out to be comets. And so then there's the question, how do we name those? And it becomes a little more difficult, trying to decide exactly when you've got multiple nights from different observatories on single nights. So, and nobody reported it as a comet, right? They're reporting it as apparently asteroidal. So,
well, I mean, reporting something as a comet doesn't mean they're reporting it asteroidal. It just means they didn't report any activity.
Right.
Yes.
Right.
But for sure, the rules for naming comets are different than the rules for naming asteroids.
They are. Yes. Yeah. They will continue to be different. So, yeah. Okay. Well, thank you very much for coming on for an interview. I think that our audience will be very interested to hear about your work, and we'll try to get this up very soon.
Okay. It's nice talking to you.
Yeah. Nice talking to you.
Thanks, Rob.
Okay. Take care.
All right. Bye-bye.